G'day guys, in this video I'm going to be doing something a little different to my typical engineering videos I usually do. In this video I'm going to be covering a fairly interesting mathematical puzzle. Let's say that we have 3 hikers here and they're stranded by a lake. One hiker needs to reach a phone 160 kilometers away to call for help. Now here's a little bit of information about the hikers. Each hiker can only carry a bag containing 10 liters of water. And each hiker walks at a constant speed and consumes 0.1 liters per kilometer. And the rules are, no hiker can stop on the path with or without water. So let me clarify by that, staying at the lake is fine, and staying at the phone is fine, but they can't stop anywhere near along this path for an extended amount of time, okay? And hikers can share water and refill at the lake. And by share water, I mean, that means when they're walking together, they can all drink out of the same bag, but one hiker can't carry 2 bags, for example, okay? Pause this video and come back when you're done. Okay, well, you might have started doing this problem by considering how far one hiker can go by himself. So let's consider this right here, this blue line, as the distance he can walk by himself, and let's say he goes a distance x1. And let's find out the largest possible value x1 can be. Well, if he consumes water at a rate of 0.1 liters per kilometer, if we get 0.1 and times it by the distance he's moved, x1, and set that equal to the maximum amount of water he can hold in his bag, 10 liters, then we solve for this and we can say that the maximum one hiker can travel by himself is 100 kilometers, which is sadly way less than the necessary 160 kilometers he needs to reach the phone. So clearly this very simple solution just won't cut it, okay? They need to work together somehow. So you might have also considered, this is the path just here, you might have also considered all 3 hikers walking together at the start, right? And let me just draw them out for you. All 3 hikers walking together at the start, and you might have said, okay, what happens if these 2 hikers supply water for this guy, and then this guy just continues the path as far as he can? So in that case, then these guys would supply as much water as they can before they need to head back, and then this guy just powers as far as he can to the very end. Sadly, if you do the math, and I won't do it for you, but sadly, if you do the math, you will just fall short of 160 kilometers. So that can't work, unfortunately. The solution needs to be a little bit more clever, and here is that solution. So let's consider the path just here. And now let's consider the same thing. They all walk together for the first part of the journey. So this is the first guy, this is the second guy, this is the third guy. They all walk together, but for the first leg of the journey, this poor hiker is supplying water to these 2 guys for the first leg of the journey before he needs to go back. So then after he does that, he needs to head back. Now these guys haven't had a single drop of their own water, so they power on. And they get to another point just here. By the way, let me mark this checkpoint as a distance x1. Okay? Now this second hiker will reach another point, which I will call x2, before he's really close to running out of water and needs to start heading back himself. But if we want to maximize the distance he can go, right, then he won't be able to go back all the way to the lake. This is where the genius comes in. What we're going to do is we're going to say this guy will refill at the lake and then come back to meet him so that he can supply water with this guy so they can head back together. That's the genius part. So let's call this distance, the distance which they meet up again, as y1. And then let's draw their path afterwards once they meet up. This first hiker supplies water and escorts him all the way back. To the lake like that, nice and safely. Now, this first hiker has quite selfishly not had a single drop of his own water from his bag, so he can continue powering on as far as he can, and let's call that distance he travels x3. And our job is to prove that x3 needs to be greater than 160 kilometers if this method is to work. Okay? So let's go through the maths now. Now that we've got the game plan, let's go through the maths and find out what happens. Okay? Well, let's consider the amount of water this poor guy, this first hiker, needs to drink in this first stretch of the journey. Well, if he's supplying water for all 3 of them, he's drinking at a rate of 0.3 liters per kilometer, right? And then he travels a distance x1 with them, so it's 0.3 x1. That's the water he drinks from here to here, but then he travels back by himself, so it's going to be plus 0.1 x1. This is the total water he consumes, and we want to maximize that, so we're going to set that equal to 10 liters, every last drop in his bag. Okay? That's one equation we can use. The second equation is, at this point, this guy hasn't had a single drop of water out of his own bag, but for this leg of the journey, he's going to be supplying water to this guy. So he's going to be drinking at a rate of 0.2 liters per kilometer, right? Because there's 2 people drinking this water. And he moves a distance x2 minus x1. That's this distance just here. And then he needs to travel back to this point by himself. So plus 0.1, because it's just him, he's drinking at a rate of 0.1, times by x2 minus y1. That's this distance. And that's the point where he runs out of water and meets up with this guy. So we're going to set this equal to 10 liters. Okay? Now, lastly, this guy hasn't had any water of his own bag yet, so he needs to try and push to the finish as fast as he can, as far as he can. So he's drinking at a rate of 0.1 because it's just him, and he travels a distance x3 minus x2. x3 minus x2, and we want to maximize that, so we'll just say he drinks every last drop of water and set that equal to 10 liters. Okay? Now you might be thinking there's a problem here. We've got 4 unknowns in 3 equations. We can't solve this. Of course we can. We just need to consider that extra equation to find y1. So this hiker just here needs to travel this distance by himself, and then this distance sharing water with this green hiker. So he drinks at a rate of 0.1 to start off with, and goes the distance y1. Then he's supplying water for this guy who ran out of water here, so he's going to start drinking at a rate of 0.2 times by y1 to go back. Okay? And let's maximize that and set that equal to 10 liters as well. Okay? So this finds out the maximum value that y1 can have, right? So at the moment they've gone as far as they possibly can. Now before I start solving these things simultaneously to solve for x1, x2, x3, and y1, let me probably tell you exactly what's screaming at your minds right now. You're probably thinking, wait, hold on. All of this rests on the assumption that by the time this second guy started going around his section of the path, the first guy may not have had enough time to meet up with him yet, right? And of course that is a possibility, and we need to write a time constraint. A time constraint to determine whether that is actually the case or not. So basically, we want to make sure that this guy can actually meet up with this guy in time. So let's consider the time it takes for this hiker to get to here and then here. Well, it takes him, let's see, this distance is x1. And then this distance here, let's say he refills his water at the lake instantly. And then he needs to move up this distance, which is y1, right? That's the distance he moves, divide it by the velocity to get the time it takes to do that. Right? And that's got to be less than the time it takes for this guy to go around here, right? So what's the time it takes for this guy to go around here? Well, this distance is going to be x2 minus x1, and this distance is going to be x2 minus y1. Right? So that's the distance he moves, divide that by the same speed, because they all walk at the same speed, right? And this is our time constraint. If this is true, that means that this can work, that they pull it off, that this type of like coordination can work. Of course, this could be quite a bit less, which means that this first hiker will have to wait at the lake for a little bit, but that's fine. He can wait at the lake all he likes. He just can't wait along the path. Okay? So let's solve this simultaneously and see what we get. Now, I won't bore you with the mathematics, but I'll just give you the answer from these equations. x1 is going to be equal to 25 kilometers. x2 is going to be equal to 61.11 kilometers. And x3, the most important value, is going to be 161.11 kilometers, right? And y1, I'll just write it over here, y1 is going to be equal to 33.33 kilometers. Okay? So this actually shows that the maximum distance our third hiker can go is greater than 160 kilometers, which means that he can make it to the phone and a little bit further if he wants to. Not that he would, but he could if he wants to. Okay? And let's see if the time constraint holds true. If you plug in these values, you get 58.3 is less than 63.89. If you get rid of the v by multiplying it out, which of course is true, which means they pull it off. It can all work perfectly, harmoniously. They can work together. He can meet up with him. This guy can go as far as he can and reach the phone with still a little bit of water left in his bag. It works out perfectly. Anyway, guys, I hope that made sense. Just so you know, I do videos in engineering dynamics, vibrations, and statics. Feel free to check that out on my website if you like. I hope that made sense, guys. Cheers.